Right, I need to get to bed, so let me just do this one. Question 9 in Sierpinski's book. I've skipped a few because I think these ones are. I haven't shown you how to do infinite sums. Sorry, infinite sums, finite sums. I think I need to show you how to do finite sums. And I yeah, I didn't know this, right? This is kind of a crazy. I did know that like 1 cubed plus 2 cubed plus. Isn't it true that the sum of the first n cubes is the square of the sum of the first n numbers? So in particular, the sum of the first n numbers divides the sum of the first n cubes, but apparently the sum of the first n cubes divides the sum of the first n fifth powers modulo some random 3. So my instinct. So let me show you how to sum the first n cubes. I'm going to need some imports. So lemma sum of cubes. Right, we've not done anything like this. So n is a natural number. I want to sum all the cubes up to. I'm going to sum up to n minus 1 because I'm like that. Because I want to use some range. Let me just show you. Check finset.range. Do we even have this imported? Yeah, we do. Finset.range. Finset.range n is the set of natural numbers less than n. That's what Lean likes to do. So Lean likes to go from 0 to n minus 1 instead of from 1 up to n. But of course, if I prove this for n replaced by n minus 1, then you can just deduce it by, using n plus 1 instead of n. So how do you do sums? And the thing you need to do is we need to open summation notation. So let's open locale big operators, I think it's called. And now I want to do the sum for I in range n. Oh, finset. Let's open finset. The sum for I in range n of the rational number I cubed. I claim that equals n times n minus 1 over 2 squared. So why have I suddenly coerced everything to q? And that's because if you don't coerce things to the integers, then subtraction is the wrong function. And similarly, if you don't coerce everything to the rationals, then division is the wrong function, right? Like if I evaluate 5 over 2, it's just the same issue. See, 5 over 2, Lean evaluates this to be 2. And the reason is that because if I hover over this div, you see has div.div, it's got this type alpha to alpha to alpha. So if it eats two things of type alpha, it's obliged to spit out something of type alpha. So if you give it two naturals and then tell it to divide them, it must spit out a natural, whether or not the answer is actually a natural. So we have to coerce to the rationals to get sort of mathematically correct division. Otherwise, subtraction and division are not sort of mathematically meaningful. So how do you prove results like this? You prove them by induction, don't you? So induction in with DHD, comma, and the base case, but probably the simplifier will do it, will it? Simp, no, hard luck, ring. That's done that. And the inductive step is kind of interesting. We'll need to do some rewrites. We know what the sum is for I in range D, and we're trying to work out something for I in range D plus 1. So if I sum up something up to D plus 1, then it's the same as summing it up to D and then adding the last term. And that's called rewrite finset.sumRangeSuck. It's a rewrite I've done. And now do you see we've got the sum to range D, which is, that says what, so we know the answer. I'm just saying you can prove this by induction. And this is exactly the induction proof. And so now we've got some mess, but this is just going to be, the ring should do this, except ring, I don't think ring can do it because we've got d.suck. So if I do simp first, and now try ring, there we go. So that's done some cubes. And next we'll do, I'm just thinking about this actually, this might not be quite as easy as I thought. Oh, it doesn't matter. And now let's do sum fifths. Lemma sum fifths. If n is a natural number. So now I want to sum the fifth power, and I don't know what the answer to that is. So that's a bit of a blow, but actually I think you can look this up on Wikipedia. So sum of, what am I going to call it? Sum of powers. I think Wikipedia has the first few. Yeah, what's Faulhaber's formula? Here we go. It is apparently. It's apparently 4a cubed minus a squared over 3, where a is. That's interesting. 4a cubed minus a squared over 3. 4a cubed minus a squared over 3. Well, I'll be. So 4 times n times n minus 1 over 2. What was it again? 4a cubed minus a squared over 3. 4 times this. I don't think I need that bracket there. 4a cubed minus n times n minus 1 over 2. All of this, crunch, crunch, there, over 3. And I reckon the proof will be, do you think this same proof will work? Oh, it doesn't. It's kind of interesting. So maybe, did I get something wrong? Oh, I'm cubing the wrong thing. 4 times, no I'm not. Oh, I miscopied. Is it 4a cubed minus a squared over 3? There's a, yeah. If I put a squared there, yeah, now it works. Okay, so now we've got those, and now I'm slightly worried about integrality. Okay, well let's press on then. So here we go. Let's see if we can actually do this. So the claim is, if n is a natural, the claim is that the sum for I in range n, and now I don't want to coerce to the rationals, I want to coerce to the integers. The sum for I in range n, or maybe I'll just not bother. 3 times, so 3 times this thing here, I to the 5. My claim is that this number here is divisible by the sum for I in range n I cubed. There. This might be harder than it looks. So I know, why don't we, so the point is that we know the answer now, because all we have to do, the answer is multiply that by 3, and then it's 4 times n minus 1 over 2. So why don't we, do you know what, this might be easy. We can use, I think it's 2 times n minus 1, minus 1. There, so I claim that that's the answer, and if it's not the answer, we might have to do some serious rethinking. But I think this must be the answer. Thank you, Wikipedia. And now I've got to prove this equality of naturals. I've got a natural subtraction. That's horrible. Ooh. Do you know what? I'm gonna rewrite that. Rewrite int div divid if. What was that? Where was that one about? I want to convert to integers immediately, right? Where did I do that? I can just search for it again. I don't want to do that subtraction because that's a natural subtraction, and that's just ring. I've got massive bells ringing in my head saying that's a bad idea. So let's do example A and B naturals. I claim that the integer A divides B if and only if A divides B. And that's in there somewhere because we found it earlier. Int coi nat divid. So int coi nat divid. And I need to rewrite this way. So now I am working with integers. And so now when I use this, yeah, you see now this is integer. You see there's integer subtraction. So now I've got to prove that these, that's an equality of integers, but now I claim, I now need to, you see these proofs aren't going to work. These proofs up here aren't going to work with integers because they've got division in. So I'll have to spend a lot of time faffing around trying to prove that if n is an integer, then n times n minus 1, the 2 actually just divide it, and I don't want to go there. So I want to prove now that this is an equality of rationals. So I need to know the name of that. I wonder if that has a name. So example, if A and B are integers, I claim that the rational number A equals B if and only if A equals B. What do you make of that, library search? Int cast ing. And what does int cast ing do? Yeah, okay. So let's try that. Rewrite int cast ing. I'm a bit worried. So I need to go this way, but then it won't know where to cast them to. Yeah. So maybe I'll put at int cast ing. 1, 2, 3. I'm going to have to overrule. I'm saying lean. You can't guess what this one is. Let's try this. There we go. And now let's try pushcast. Great. And that's pushed the cast all the way in here. And now I will be able to rewrite some cubes. Oh, what I was going to say. I want to go home. It's bedtime. There, and now I rewrite some fifths. There, and now that should be ring. Yeah, excellent. Right, I've just recorded loads of videos. That was a really fun way to spend a Saturday, to be quite frank. And I'm going to bed because I'm in a really cold shed. So night, and maybe I'll upload these first. Cheers, and thanks for watching. I don't know how many of those you stuck through, but I hope they've given you some kind of idea as to the kind of tools you'll need to do number theory.